Hi, my name is Armando Diaz, and this is a presentation for the class Advanced Algorithms. And I will do the review of the paper ETA prediction with graph neural networks in Google Maps. This paper was published by DeepMind and Google. And let's start with the problem statement. So I will start defining ETA. So ETA stands for estimated time of arrival. I believe most of us have already used Google Maps. Google Maps has or requires two main inputs. So the first one is an start point, and this start point can be based on your current location using your GPS, or it can be tied by the user too. The other input is the endpoint. This one is just the destination of the trip. And as we can see here on the images, we can see that there's gonna be multiple routes to arrive to the destination point. So these routes are gonna have different estimated time of arrivals. Um, the goal of Google Maps is to provide different recommendations and predict and increase the prediction or the accuracy of the prediction of the expected travel time. And this prediction is going to be based on current and historical road network conditions. So let's say, for example, that there is a lot of traffic, and this traffic can be uh, based on the weather. For example, there is a lot of rain, or maybe there is a crash. So all of these data points are gonna provide feedback and insights to the model. And this application, or just increasing the accuracy, is very, very important for all the users. When we talk about users, we are talking about normal drivers, ride and sharing delivery companies, for example. So all the users who are relying in this application. So let's now um, dive into the proposed solution. So Google wants to enable scalable traffic predictions with graph neural networks. Um, the word here, scalable, is super important because Google Maps, or many of users rely on Google Maps. With many, we are talking about millions of users. So Google Maps needs to be good enough to provide the best precision and accuracy in the recommendations and routes. So this is something that the authors are concerned, and that's one of the reasons why they decided to use a graph neural network. So if we think about the traffic maps, the traffic or the transportation maps can naturally model as graphs, as you can see here. So let's say, for example, that the nodes can be intersections and the edges can be roads. So just by mapping the real world into a graph, we can see that the modeling is going to be very straightforward. Now, if we go to the GraphNet is based on super segments. I will explain what a super segment means in the next slides. But for now, we just now know that the GraphNet is going to require as an input different super segments that are pretty much based on multiple segments. um, these segments describe the traffic density, for example. So let's go ahead with the problem setup. So first of all, let's define what a super segment means. So by the definition that Google provided is as follows. So it's a sequence of connected route segments that follow typical traffic routes. So if we look at the image on the right, which is the segment in this case is defined as 10 meters. And if we look at the super segment, we can easily infer that this super segment is gonna contain multiple segments. In this case, the super segment has a distance or of 3 kilometers, for example. So now the super segments, this is a table of how the data is structured for all the data sets that were used for simulation and experimentation purposes. So if we see on the left, we can identify that the first data set um, is pointing out to Los Angeles. The second one is New York City. The third one is Singapore, and the last one is Tokyo. So this different series, as we can see here, we can see the number of unique super segments per city. We can also see the average of number of segments per super segment. So we can see here that this average goes from 18 or between 18 and 24. So this is a very similar number per super segment, and also the average segment length. This one goes between 57 and 109. So this is just a description or the statistics of how the data set looks like. Now, if we now I think it's time to explain what are the features that were used for modeling purposes. So the node features, for example, these are the road length, the current speeds, and also historical speeds. Now, the data sets are anonymized, and that means that is a crowdsourced real-time and historical traffic data. This data is not as reliable as a physical speed sensors, for example. However, it is enough, is good enough for uh, predicting in near future predictions. So if we needed, for example, to uh, perform real-time predictions, maybe this data would not be the best to test and also to perform the predictions. So this is not a big problem so far. Now the traffic conditions, as we know, change dynamically and are unpredictable. Most of the trips run between 10 minutes to 1 hour. So that means that we don't really need a real time a predictor model. And the same thing is that we don't need predictions in the long term, like let's say 1 day, 2 days, 3 days, 4 days, like, or 1 month, 1 year, for example. So the closest the the closest we are gonna make the prediction, the closest is the horizon, is gonna be easier to have a better accuracy for the model. Um, Now, the model training, uh, this is the architecture implemented by Google. So it is composed of an encode process decoder model, and the encoder uses the input, which is X, and it converts this information into different vectors. Then the processor is composed of multiple layers, and it's going to use this vectorized information and normalized information to perform different operations. And the decoder is just going to take the information that came out from the processor and then decode the vectorized data into data that can be interpretable. So the processor has three main components. So the first one is messages on edges, and the second one is aggregate messages, and the last one is update nodes. So these are the three steps that the processor is continuously doing while it receives like new data. Now the quantitative evaluation is based on RMSE, and this is just the metric used by Google to identify the error or the performance of the model uh, over the other models. So we have here the different regions. We have New York City, Los Angeles, um, and the other cities. And the first one is compared with the real time. So while you are driving, if you have used Google Maps before, you can see the well, an estimated um, uh, time of arrival. Then we have also the historical data, and then we have the deep sets. That's a different model, and then we have the graph neural network. So as we can see here, we are looking to minimize this value. So the graph neural network has the minimum value across all the different measurements. This is just very good, which means that it outperforms all the different models, and is that's one of the reasons why Google is currently using this model uh, over well, is deployed this model worldwide. Um, we can see now the same evaluation, but across different horizons. So an horizon is just how much time ahead you wanna make the prediction. So let's say horizon zero is, let's say that is our current start point, and the horizon three thousand 600, it can be the amount of minutes ahead that you wanna predict, for example. So we can see here the graph neural networks outperform the other uh, different metrics too. So this is the performance of the model. Um, however, however, the data that is used and is coming from the traffic conditions is very noisy. So in order to smooth the distribution of this noisy data, they use two different methods. So the first one is meta gradients, and the second one is the exponential moving average. So these two different methods, as we can see on the right and the charts, the distributions just got a lot smoother, and that smooth is just gonna help the model to train a lot better and to understand like better patterns. So now we can look at the results. As we can see here, we have two different charts, one above, one below, and the first one is comparing the departure time versus the travel time. The second one is doing the same thing, but the first one in particular is comparing how the current model, which is GN, is comparing with real time and the actual value. So the real time is the brown line, and we can take a look here. The model or the proposed solution is very close to the actual value, which is actually incredibly well done. And then if we see the other chart below, and this one is comparing the same information, which is the model, but and the actual, but in different horizons. So as we can see here, we can easily see how the the model is gonna be predicting the same information or the same routes in different times or different horizons, and that can help the model actually to identify how this distribution of estimated time of arrival is going to look like in the future. So it can actually take that information, like use that information as feedback for the model and improve just the accuracy of the prediction. So this is how the results look like. Now the returns of this model. This model is already deployed worldwide. Um, Also has been reducing the ETA, which is a great improvement worldwide. So as we can see here, the values uh, in decrease 16% in London, which is the minimum, and the biggest one is 51%. So that's the performance that Godin increased worldwide, which is really good results. Now, what were the challenges? As I mentioned at the beginning, one of the main goals of Google is to have a model that can be scalable. Um, so latency is one of the main requirements. In order to meet that latency, they catch the predictions every 50 seconds. So that means that every 50 seconds they were recalculating the predictions. So they found out that actually they could extend those 50 seconds up to 2 minutes because the conditions or the raw conditions doesn't change a lot in that particular amount of time, and it doesn't affect the accuracy or performance of the prediction. Also, they the speed the speed was very specific for busy segments. And so let's say that you are in the road, there is like a car accident, for example. So this can cause the different. I mean, the same route in the same route, you can have different speed distributions. So in order to improve the accuracy, they had to use the specific speeds based on the users. So that was just like a tuning for modeling. And now in the coverage, they found over 1 million of super segments, which cover most common routes in metropolitan areas, and the rest are defined as per segment models for less visited road segments, which makes sense here. Um, and in conclusion, this is the overall pipeline. So the first thing is the anonymized travel data, which is analyzed and it extracts all the super segments over all the routes using the traffic maps, and then this is used for training purposes using the graph neural network. Then there is another feature which is called Pathfinder. Basically, the user or candidate can rank or can choose the route based on the predictions. This information is ranked by ETA, and once you have what is um, the best route, this information can go directly to the Google Maps API or the Google Maps application, and that's how users interact with the results of this model. So that's it. Thank you.